My name is Taemin Park, and I'm from UC Irvine. And today I'm going to talk about NoJITsu, locking down JavaScript engines. This is the joint work of the UC Irvine and KU Leuven. So JavaScript engine protection is important. Basically, every browser has JavaScript engine, and it automatically runs any script embedded in any web page. So people are always open to threat to run the attacker script, which can trigger a vulnerability inside of the JavaScript engine, and so that attacker can run some arbitrary function or arbitrary system call. So one of the famous attack on JavaScript engine is spraying attack, where attacker encode his malicious code inside of the huge number of the constant. When this script is cheated, those constants are sprayed all over the heap. Of course, it doesn't have any harmful effect in normal execution, but attacker can trigger a vulnerability to change the floating counter and jump into middle of the cheated code where attacker's code resides. So there are more advanced attacks and defense on cheated code, especially utilizing race condition. When JIT compilation unit try to compile a script into JIT-IR, which is the intermediate representation of the cheated code, attacker can spawn a new thread and steal the CPU cycle to override the JIT-IR, which later be transformed into cheated code. Or attackers use the same technique to directly override the cheated code when the right window of the cheated code is opened. So people suggested several solutions, mostly isolating JIT component by separate process or trusted execution environment. And those are attack and defenses on the JavaScript engine heavily worked on, but they are all about the JIT. But the basic execution unit of the JavaScript engine is interpreter. So we start to think that it's possible to corrupt the interpreter to run some arbitrary function or arbitrary system call, and it is bound to be possible. So here's our contribution. We developed the instance of the bytecode interpreter tag, which corrupted the core data of the interpreter to change the behavior of the interpreter execution. By doing this, we successfully execute arbitrary system calls. So in order to protect the JavaScript engine from the bytecode interpreter attack, we suggested defense, NoJITsu, which enforces fine-grained memory access control over all important data. So it protects not only cheated code, but also other core data in JavaScript engine. And we evaluate our defense, and we prove that our defense is practical in real world. Before going to talk about attack and defense, I should go over how JavaScript engine execute and what are the core data inside of the JavaScript engine. Look at this slide. When a script is about to be executed, it is compiled by bytecode compiler, which generate bytecode object table and JavaScript object. Bytecode is the stream of the bytecode instructions, and those bytecode instructions are executed by the interpreter one by one. The bytecode instruction is similar as a machine instruction, but difference is that the operand is not used to specify register number or direct data, but instead it is used to specify an index of the object table, which point to JavaScript object where actual data is stored. So when certain portion of the bytecode are executed many times to speed up the execution, JIT compiler compiles those portion of the bytecode into JIT-IR, which later be transformed into cheated code directly executed by the CPU. Here we all know that the JIT-IR and cheated code are important because there are so many researches on them. And here we argue that bytecode object table and JavaScript object are also important, and especially our attack and defense target them. Here's our bytecode interpreter attack. Especially our attack corrupts the function call routine of the interpreter to run any system calls. And we implemented our attack on the SpiderMonkey, which is one of the famous JavaScript engine for Firefox. Our threat model is as follows. There is at least one memory corruption vulnerability, which gives the attacker an arbitrary read and write capability. And we assume that code injection defense is deployed, which means memory region should be either writable or executable. And lastly, our threat model has lightweight code reuse defense, which includes ASLR and coarse-grained CFI. And I will illustrate our attack by giving an example. This full exploit is developed by our second author, Karel. So thanks, Karel. So look at this slide. This is the attacker script, which calls function foo, where the cosine function is called. When function foo is compiled, it will generate the corresponding bytecode, object table, and JavaScript objects are generated. The calling of cosine function is achieved through indirect function call, where the function address is fetched from function object, and argument is fetched in the same way. And also, this indirect function call gets the address of the context object as the first argument. So here we add a code to trigger the vulnerability. In our implementation, we use the recently discovered type confusion vulnerability that gives an attacker an arbitrary read and write capability. So attacker can find any object in the heap and follow the pointers to find the function object and context object, and corrupt the function object with the address of the system function, and corrupt the context object with any shell command. So when function foo is executed, instead of the cosine function, the system function with the shell command will be executed. So we successfully run the system call here. So in order to protect the JavaScript engine from the bytecode interpreter attack, we suggested NoJITsu. Our NoJITsu enforces fine-grained memory access control through Intel memory protection key. Let me talk a little bit about Intel MPK. This is a new hardware feature to control the protection of the memory. It doesn't have any involvement in any system call, and it doesn't need to change the permission bit of the page table, so it's very fast. Look at this slide. Each memory chunk is assigned with up to 15 kinds of the keys with associated permissions. So when someone wants to change the permission of the chunk, the only thing he has to do is that change the permission bit of the specific key at PKRU register. And then the memory chunk of the same key are affected. And also, MPK support execute-only memory, which mprotect cannot. And finally, the MPK is thread local, which means that each thread has a different view of the permission of the same chunk of the memory. Yeah. Now I'm going to apply the nice property of the MPK to the memory policies in JavaScript. Here's the legacy one, where bytecode object table, JavaScript object, and JIT-IR are all time readable and writable. So they are always open to be corrupted. And JIT code is readable and executable, which means that attacker can harvest the RP gadget for attacks such as JROP. And also, the JIT code becomes writable temporarily when it is emitted to memory. And the attacker can utilize a race condition to overwrite the JIT code. So in NoJITsu, we try to minimize the permission of those data as small as possible. So now, bytecode object table and JavaScript object IR are all-time readable, and we make the JIT code execute only. On top of that, we separate the chunk of the memory into different kinds and assign the different MPK key to manage them individually. For example, if there's a write instructions on JavaScript object tables, we only open the write window for those instructions, so the other data kinds are not affected. Also, the race condition attack is no longer available because the write window is independent from the attacker's thread. But there are challenges we need to tackle. It is required to open the right window for all the right instructions for those data. But finding those right instructions is not trivial. And also, implementing protection changes for those right instructions is very difficult. So let's go ahead with the easiest one. We found that the bytecode object table, JIR, and JIT code are only writable during the compilation. So we manually find those right instructions and implement the protection changes before and after them. But it's not trivial to make the JIT code execute only, because JIT code is a mixture of the machine instruction and readable data. So we separate JIT code into machine instruction part and readable data part and assign different key so that we make machine instructions execute only and readable data read only. And let's get to the most difficult one, the JavaScript object. There are so many JavaScript objects, and there are so many write instructions to JavaScript objects, so it's impossible to find everything manually. So we can rely on the static analysis, such as pointer analysis, but it is found to be very conservative, and it's going to widen the right window significantly. So that's why we decided to rely on dynamic analysis. Our dynamic analysis is basically instrumented code for the auto write instruction using LLVM. And this instrumented code check whether those write instruction touches on JavaScript object. And we run this instrumented JavaScript engine with a well-defined input set while making JavaScript object read-only. So when a write instruction tries to write on the JavaScript object, it will cause segmentation fault because they are read-only. And it goes to our custom signal handler, which check whether it is the MPK violation or not, and change the permission of the JavaScript object writable. And it goes back to our instrumented code and check whether the permission of the JavaScript object is changed. If it is, it means that the write instruction above touches the JavaScript object, and we report the location and function. And finally, we make the JavaScript object read-only so for the rest of the analysis. After finding all the functions, we implement the protection changes using the LLVM. Basically, we open the write window at the start of the function and close the write window at the end of the function. So we open the write window for entire function. And also, we could find some optimization opportunities in some cases where those kind of functions are called many times in the loop. So in this case, we hoist those protection changes out of the loop. In order to find all those functions, it's best if our input set guarantees the full coverage. However, it's impossible. So we studied the JavaScript engine, and we found that those functions have commonalities, and we categorized them into 4 accessor functions. And those accessor functions work as gateway to write on the JavaScript object, and they are extensively shared among the other components of the JavaScript engine. So the only thing we have to do is to find all those accessor functions, and we believe that the extensive test cases on the JavaScript object eventually find all the accessor functions. That's why we decided to use JavaScript test switch as our input set. And we're going to prove this one in our evaluation. So this is our evaluation. I'm going to evaluate the coverage of the dynamic object flow analysis. In this analysis, we just pick up 1/6 of the test suite as input set for dynamic analysis and implement NoJITsu. And then we run NoJITsu enable the JavaScript engine with a full test suite. And we found that it passes all the test cases. So even a small subset of the test suites are enough to find all the access function. We also evaluate whether our defense defeat code reuse attack and bytecode interpret attack. And we actually fully implemented fully working GLOB and tried on our NoJITsu-enabled JavaScript engine. And we found that it fails because the GLOB attack tries to read the JIT code, which is no longer readable anymore. And also, the bytecode interpret attack is not available because now JavaScript object is read-only. We also evaluate the performance of the NoJITsu. Especially, we use the long spider benchmarks, which is available at WebKit. And we run those benchmark on Intel Xeon machine under Ubuntu 84.1. And here's the result. X-axis is benchmarks, and Y-axis is performance override induced. And blue bar is NoJITsu without hoisting optimization, and orange bar is NoJITsu with optimization. And we found that there's on average, the 5% of the overhead is induced, and it becomes 3% with the hoisting optimization. Actually, our hoisting optimization widened right window, but it is negligible. And I'd like to ask you to check out our paper for the right window analysis. So I have to conclude my talk. We demonstrate a new bytecode interpreter attack, which corrupt the core data of the interpreter to run the arbitrary system calls. And so that we propose NoJITsu, which enforces fine-grained memory access control using Intel MPK. And we evaluate our defense that we prove that our defense is effective in code reuse attack and our bytecode interpreter attack without incurring much overhead. This is the end of my talk, and thank you for attention.
All right, questions from the room, come line up at the microphone. And if you want to give you boy a job, then line up during the coffee break.
Thank you for a great talk. Ramadi from UC Irvine. I just have a clarification question for you. So if I understand correctly, you were saying that it's not possible for an attacker to attack the JIT code during the write window? And why is it not possible to do so? Say if an attacker is following tightly the write windows, like they monitor the write windows, wouldn't it be possible to attack the...
You mean the attacker spawn another thread for using the race condition, you mean?
Maybe, yeah.
So because the MPK is thread local, so every thread has a different view of the protection. So some certain for certain thread, the write window is open, but the other thread, the write window is not open. So the other thread has the basic permission of the chunk of the memory that is only read only or execute only. So that's why attacker cannot overwrite.
So you're saying since the attacker is in a different thread, that's why it's not possible to attack?
Yeah, sure. These days, there are so many attacks papers that usually exploiting spawning new thread. So that's
Thank you.